So we're very happy today to have Josef Gonzer, if I pronounce it correctly.
Thank you.
Who's going to tell us about his recent paper on statistical games. Right?
Yes. So thank you very much. I'm very happy that I got this opportunity to present my work to you. And if you open the PDF, then you've seen that it's pretty long, and it will be a challenge to summarize and discuss this in 1 hour. But I hope that I will be able to bring you some thought-provoking ideas, and that it will be useful for you sometime, somehow in the future or the present. We will see. Okay, so the title is Statistical Games, and I try to summarize in the beginning the why, and there will be two answers for this. Or there is a mathematician answer. One is why not. The other one, it might appeal to some. So this is actually a quotation from Abraham Wald, who was one of the pioneers of writing about game theoretical decision functions in the 1950s. Then in the first part, what I will show, this is established mathematics. Nothing crazy is going on there, and you can have elementary calculations resulting sometimes surprising results. Hopefully, you will like those, and it can be continued to the more interesting things like optimization in functional spaces. If you let these parameters to be continuous, I will not talk about this, but this is a very natural generalization. And from I will not show proofs here. So for that, I advise you to see the paper and the appendices mainly. But you can see very nice mathematics in these expansions, inequalities, and all these, which can be used to actually say something meaningful. It has a quantum generalization. I also not discuss this, but if you want, I can tell you where you can generalize the structure and how this could be quantum. It would be a quantum methodology, more or less. And then it's just fun to design concepts which are grounded in their ability to simplify proofs and calculations. Oh yeah, and I want to encourage you to have questions. So there is a lot of material here. There will be examples, plots, etc., etc. I can jump those, and we can diverge to any direction. So feel free to interrupt me, please. Okay, so and there is a philosophical answer. I really don't want to bash any other frameworks or approaches, but sometimes some might have this feeling that statistics is something what is useful, it works, but it's somehow seems like or feels like a set of ad hookeries and a set of fixings. And so what I try to do here is to make it a little simpler, a little more coherent, try to find some kind of organizing principle in statistics. And as I was also interested in this concept, which is uncertainty. It appeared in the beginning of the 20th century in economics literature, different other fields, but it fell out from favor, basically. And now people are talking more about risk than uncertainty. Some even question if uncertainty is a valid concept. And I want to go from epistemology, so about talking about what we know, what we should think, and things like that, to strategy, which is about what to do. And finally, I want to talk about what if we would change priors in these Bayesian frameworks to fictional players, basically. Okay. So I will give a very, very oversimplified introduction to game theory because this might be useful. If you want to skip it, then we can. So I don't insist.
Yeah.
Okay. So here, what I summarize is the minimal setup. Here we assume only 2 players. Those can have 2 action sets, A1 and A2. We assume as physicists that those are finite. There will be situations where are not finite, but still we will assume that, we will assume that our intuitions about finite action spaces actually are valid. Then for rigorous proofs, see the appendices. So if you have 2 players and they have 2 action sets, then they can do actions. From these actions, you can derive, there can be consequences of these set of actions. In usual introductory game theory, they don't talk about this abstract thing, which is consequences here. I introduced this because we will talk about some gambles where money can change and things like that. And this consequences is something close to states in reinforcement learning, for example. And then what is maybe more important for the agents, there is a utility function, which associates utility to consequences, or you can go back to the set of actions. So what is utility? Utility is an abstract value. It's not money. It's inherently subjective for the agent. And it's like a hidden function. So if I want to be very sincere, if I want to know what is the utility function of an agent, then I need to observe its behavior and try to find out what kind of utility function could describe that kind of behavior. You can have guesses, but it's inherently a subjective thing. And there is a misconception that in game theory, the agents are selfish. So no, it is totally okay. So it's totally fits into the framework if an agent is totally interested only in others' welfare. You can totally construct a utility function like that, and you can build up game theory to that. There is no contradiction.
So the utility function is something which is it given in a specific problem, or is it something that you?
So in the mathematical framework, we assume that it's given. If you have a real life situation, then you need to either have an estimate or some kind of calibration for that.
That's an example of like a really simple.
So if you in biology, for example, there is a relatively, you can understand a lot if you assume that the utility function is the fitness of the animal, which basically means the reproduction rate. For humans, economists sometimes assume that money is either proportional or very close to utility. Some other social sciences that might be other drives, fear, hunger, striving for power, whatnot.
This is some objective function, some loss function in the concept.
Yes. Okay, so this is the utility function. And then you assume that these agents can have strategies. Strategy is a probability function on its actions. I denoted this by this curly P. If you know any better notation for probability spaces, let me know. It's not easy to find a set of probably measures some. Okay, then you have this concept, this expected utility. The expected utility is the expectation of the utility of a given agent. Okay, and then you can ask that if these agents are having their own strategies, then what would be the expected utility if the agent would do action A1? And so this is expected utility A1, comma sigma 2. Sigma 2 is a strategy. Is this clear? Okay. Now, further concept, this Nash equilibrium. So a Nash equilibrium is a strategy profile. Here, this is just a pair of strategies. And we say that a pair of strategies is Nash equilibrium if there is no, if no player's expected utility can be improved by changing its own strategy. So they are in some kind of shared situation, and nobody can change its own strategy in a way that he would get better in the end. Okay, and for finite action sets, this at least one Nash equilibrium always exists, but it's not guaranteed to be unique. There can be multiple Nash equilibrium. Okay, and just a philosophical side note. So philosophically here, we are talking about this expected utility theory. It says that the utility is subjective, but agents are behaving in a way that they want to maximize the expected utility. This is not, I mean, philosophers can debate on this, but this is kind of a robust concept, and we will assume this. We will see what can bring this view. Okay, so I will read this, and there will be a better form. Now I just want to say now I talked about the why. I want to talk about the what. So what I wanted to do here is to investigate the toy model. So I wanted to see the simplest possible game where these kind of statistical concepts can emerge. And so this is not that useful if you want to do field work in statistics or something like that, but this is the minimal approach. It's like a minimal model, a toy model. Okay, and so there will be three main games. This is the first game. This is so-called Fisher game. And here the concept is that there are two players. Player one is the guesser, and player two is the chooser. And the chooser is choosing a scenario A or B. But then she also needs to generate a sequence, a binary sequence. If she chose scenario A, then she needs to put Ka number of ones into the sequence. If it's B, then she needs to put Kb number of ones into the sequence. Then the guesser, player one, can come, sample some bits from the sequence, and based on the sample, make a guess if it's A or B. And if she guesses correctly, she wins. If she doesn't, then the other player wins. Yes?
So you have some number of zeros as well.
Yes. Yeah. Yeah. So m minus Ka and m minus Kb is 0. Yes. So here is maybe a better representation. first player 2 is choosing A or B, then she needs to generate the sequences, then player 1 needs to sample from this M-long sequence, and based on the sample, guess the scenario. And if she can guess, then she wins. If not, then she loses. Okay, is the game clear? Okay. So let's see first the statistically trivial example. What happens if there are no sequences? Just one player is choosing, the other player needs to guess. So this is actually an ancient game in North America. It's called the hand game or the bone game. And I just want to ask, what would you suggest for the guessing player, and what would you suggest for the choosing player, what to do in this trivial game?
So the trivial game is where you have no sequence. So what's happening exactly? You just have to guess whether it's A or B without any input.
Yes. And the other one needs to choose without any fear of revealing anything about the sequence.
Those strategies will be uniform distribution.
Right. So anybody who played rock, paper, scissors or some other games know that if you always play A, then the other party will learn it, and then you lose your advantage. You can only, so what you can deduce, but I want to point out that this is actually a paradox. So there is no deterministic function which is useful for you in this game. Because if the other can also calculate what you would do, then you lose. So you need to come up with something which is complex enough that it's very hard to predict, and that's how you will not lose your advantage.
So here, obviously, we're talking about a sequence of games, right? So you're running this over, I don't know, 50 iterations, and then the winner is the one who's won the most time.
So this is a very good question, and in the framework of game theory, it can be a one-shot game. So even if it's life or death, and you will have only one chance to play this, even in that case, it's not good if your action is predictable, right? So yes, maybe you learn it in a longer sequence, how to actually generate these complex sequences. But even if you don't know that this will be continued for a long time, even in that case, you might put some effort to make your choice less predictable. So even in advance, you can deduce that you should act random. And even in advance, you can deduce that the other might act random. Okay. So yes, if we put it to game theory, where we assume a lot of things, we can calculate this, and it comes out that the Nash equilibrium profile is 50-50 in actions and 50-50 in losing and winning. Okay. This V star is the winning rate, by the way. Okay, now let's see the simplest non-trivial case. Now let's say that the chooser needs to generate a too long sequence, 2 bits. If she chooses A, then this is all 0. It needs to be all 0. And when she chooses B, then she needs to put there 1, 0 and 1, 1. Okay. So here,
the order doesn't matter.
she can put, the order matters. So she either chooses 1, 0 or 0, 1. Because then Yes. Okay. Because then player one can come and say that, okay, I want to see the first bit, or she can go and say, I want to see the second bit. And then it
What I'm
needs.
saying it's up to player A to determine what sequence they want to put forward. They just have to have one.
Yes. Yes. So both are allowed. So 0, 1 and 1, 0.
So that's part of the strategy of player A to determine how they will put.
Yes. Yes. And then the guesser, so she has a little more rich action set. She can pick a sample, which bit to investigate, and then based on what she sees there, she can determine if she chooses A or B. Okay, so if you do this,
The number of guesses probably is a function of n, right? So
yes, so you can do this combinatorically. Here, the max the all action set is 8 actions, but here because 2 times 2 to the second. Okay, but here I factored out a few, because if you see 1, then you surely shouldn't guess A. Right? So that's how you can factor out a few actions, the obviously wrong actions. Okay, I just put it here. Whatever you can calculate this, and the interesting thing is that actually it doesn't have only one unique equilibrium. It has a continuum set of equilibria. So there is actually a parameter which you can tune from 0 to 1. So it's the jargon is that it's a degenerate game. But maybe what is more illuminating is to show the symmetrical case, when player 1 is sampling uniformly from the first bit and the second. And so here, what happens, I mean, this is based on a calculation, is that player 1, so the chooser is choosing A with probability 1/3, B with probability 2/3, and then the guesser is sampling uniformly. But then if she sees 0, then she chooses A with 2/3 probability, B with 1/3, and then if she sees 1, then she chooses B for sure. Well, this is what comes out. Maybe a little intuitive. So A is very regular. You shouldn't choose that often, or at least some kind of what should be bigger, what should be smaller. Maybe those are things what you can guess, but the exact numbers are based on calculation. Okay, and we worked a lot to see a plot at this stage. So this tries to represent the equilibrium. Here you see tiles. The rows are chosen by player 1, the guesser, and the columns are chosen by player 2, the chooser. And what you see, so the sizes of these tiles are based on the probabilities, how these scenarios are played. So what you see there is that A is played by 1/3, B is played by 2/3, and then if she chooses B, then those other columns represent these different orderings of the bits. And then on the rows, you see one strategy when this is in a critical point, then she chooses A, then this phi check is when the critical point then chooses B, and then the other subdivisions are the sampling strategies. You don't need to understand that fully, yes?
Assuming that, so this represents just one Nash equilibrium.
Yes.
Of the, is it simple to describe what the other spectrum, what are the other?
Yeah, that could. I didn't do that because I have very strong arguments that the symmetric Nash equilibrium is very special. And the other ones might be calculated, but I see very little point to do it.
I'm sorry, just another follow-up. So in this case, the probability of winning, I'm guessing it's 50-50.
No.
Okay.
I'm not sure what it is. I don't. If you really, oh yes. So basically, you just need to investigate what's the portion of yellow and blue. So it's 1/3, 2/3. The guessing player will win more because now she has some information which the choosing player needed to reveal.
What does symmetric equilibrium mean here?
The symmetric equilibrium means that the sampling and the choice of these binary sequences are uniform, basically. So if you go to the paper, you will see that there are some non-uniform solutions as well. But those don't cause trouble because the expected winning ratio is the same. So you cannot do better if you do some exotic kind of gameplay here. Okay, now we jump a bit. This was the simplest example, and now we try to figure out what's happening in the general case. So one can come up with an ansatz here that let's assume that scenario A will be played with probability P, scenario B probability 1 minus P, then player 2 will will choose the sequences uniformly. And then player 1 is sampling uniformly. And there will be a critical value of ones, is K dot. If the number of ones in the sample is smaller than K dot, then she chooses A. If it's bigger, then she chooses B. And if the number of ones is exactly K dot, then she will choose A with probability nu and B with probability 1 minus nu. Well, this is an ansatz. You need to calculate, and you need to prove that this is actually a Nash equilibrium. This is happening in Appendix A, and it works. And you can have a theorem which says that these K star, nu star, P star parameters can be calculated from the integers of the game, and you can introduce these pKa, pKb probabilities, which are just hyperbolic probability functions, hypergeometric distributions. Then you can calculate this P star at this critical point. The nu star, I don't know any nice way how to describe it. It's what it is. And then the critical K star is the first integer where this sum becomes greater than 1. fun fact that this is actually the median of the mixture of these two probability functions. The median is not that, how to say, over-advertised in statistic courses or probability courses. This is the place which divides into half the distribution, basically. It comes up more often in game theory and other places, but not really in standard probability theory courses. Okay, so that's it. It works, and if it works, then you can start to calculate things. So here I just show nice plots to please you, where for some games you can generate these strategy plots, what I showed for this simplest example. And then these start to reveal some nice patterns. I mean, some of the patterns come from this lexicographic ordering of the sampling and the choice of the sequences. I'm not sure how much time you should spend with, I don't know, measuring and calculating the fractal dimension and stuff like this of this thing, but I think it's nice, at least. Okay. The other things what you can calculate is these equilibrium parameters. So here around 5,000 games are calculated. And so these are all matrix plots, basically, or array plots. These are not continuous. These are 100 by 100 grids. And we also said that in the beginning, we assumed that Ka is smaller than Kb, that in the scenario A, there is less ones than in B. Here we generalized it to the other situation as well, basically for aesthetic reasons, because that's how we get squares and not triangles. Okay, and so the first one is P star. We talked about that. K star is this critical number of ones. Nu is this probability how you choose if you exactly hit this critical amount. Then V star is the winning rate. What's the probability of winning for the guesser? And then this S is an interesting thing. This is a combination of K and Nu. Basically, we sum those up. We say K star plus Nu star. And it might sound arbitrary at this stage, but if we will do some limits, then it will turn out that this actually is a continuous variable in some limit. So this is a good choice of combining these two variables.
What is the interpretation of that variable? Like, is there
this S?
Yeah.
So if you know S, then you can reverse engineer K and Nu. So K is an integer. Nu is a probability. This goes from 0 to 1. If you add those, then from S you can take the integer part and the fraction part, and those give you back the critical K star and the fraction Nu part. It doesn't have much deeper interpretation than this. What will turn out that actually it helps you to determine limits. You could do any continuous transformation of this, but this is just one good choice. Okay. Okay, and so a few things just emerged, which is present in frequentist or Fisherian or Fisher Neiman-Pearsonian statistics. So first of all, sufficient statistics. Very conservatively saying, statistics is just functions from the state space. So for example, the average is a statistics because many different samples can have the same average, and it gives you some aggregate information about the data, what you got. And so what we see here is that in theory, we could take into account everything about the sampled sequence. We could take into the account the exact order of the bits, everything. But in the end, what matters in the equilibrium is only the number of ones. It doesn't matter which order they came. What's important is the total number. And basically, this is a sufficient statistics for this sampling problem. Then there is this type 1, type 2 errors. It turns out that this is basically the winning rate, assuming that the chooser was choosing A, and the winning rate assuming that the chooser was choosing B. If you frame this in a hypothesis testing framework, and you say that my hypothesis is that scenarios is A. And what is nice is that in a paper, a very early paper, I think 1933, yes. Neiman and Pearson described an imaging test where the test result, where the sum of this type 1 and type 2 error, the sum of type 1 and type 2 error is independent of the probability of choosing A or B, or choosing the hypothesis or the other. And what we have here is precisely that. So you can read the paper. This was the first definition. And this was this definition A. What would it mean that H0 had a value independent of the probabilities of P A and PB? And he writes about that. Basically, he concludes that this is very hard to calculate, and he abandons the concept, and then he searches for other nice concepts for statistics. But we here basically just constructed a lot of decision functions which has this property. Okay. Random sampling, this was one of the selling points of Fisher. It appears naturally here. Emergent probability distributions. So here you see that there was we didn't put in any stochasticity into this game. There are no coins, no dice, nothing. Only by the interaction of the players, you can somehow a probability function emerges. Okay. Randomized policies. This is something what I never seen anywhere else. I heard about suggestions how you should round up or down at rounding, but I never heard about a decision function or a test, a statistical test, which would tell you that, well, under some circumstances, just randomly reject the hypothesis. Or so this is I think this is something appearing here. Yeah, and maybe I don't mention this interpretations. Okay. So now let's assume that we go to a different place, a different casino, where it's not just one-shot games, but you have some kind of capital, and you can place some parts of your capital to some outcomes, which can come out with different probability. Okay, so I want to just very quickly ask that if there would be a casino where you know that there is 1/3 probability that A will come out and 2/3 that B will come, then what portion of your capital would you put to A or B if there is one round?
100%.
Okay, and what portion of your capital would you put if there would be 10 rounds and you need to tell a portion in the beginning, and then in every round we will put that portion. We will reinvest your money in that portion.
Including the winnings from previous rounds.
Yes.
Okay.
I mean, just gut feelings. You don't need to calculate anything.
That feeling, I would do the same as before. Well, yeah.
So all in. Interesting.
No, you lose it if you lose.
If you lose,
Lose
you're
everything.
done.
Yeah.
No, okay, I missed that part.
Take a tenth of your money and do strategy with that.
Mm-hmm.
Very conservative.
Okay, but you maybe feel that some kind of
Oh, they all independent events.
yes. But maybe you feel that if this is repeated, then you start to have other thoughts than just all in to the biggest probability, right? And of course, humans are complicated, but there are some tools in this expected utility theory why this can be handled. And one way to handle this is to say that we don't value maybe only the amount of money what we can win in expectation. Because if you would say all in, then with almost always you have zero, but sometimes you have a stellar win. And in expectation, that would compensate you if you would value only the amount of money. If we assume humans are valuing, let's say, the logarithm of their wealth, then not the all-in strategy is the best for you, but some kind of splitting. In logarithmic, if it's logarithmic, then in this scenario, you would put 2/3 to B and 1/3 to A, right? Okay, so it's a mistake. Don't be afraid of that long definition. This is now we define the so-called Bayesian games, okay? So the Bayesian game is very similar to a Fisher game, but here you don't need to guess A or B, but you need to put some portion of your capital to A or B. Okay, so here you don't need to put all in to either, but you can hedge, you can stay in the middle. Okay, and so this P prime parameter will be the splitting ratio, how you split your money between A and B. Okay. So now, technically, this is a big change because now the action set is not discrete, not finite, but it's continuous. We lose a lot of good theorems, good general theorems in game theory, but you can do direct calculation, and then it can be shown that this has one unique Nash equilibrium. Okay. So here you see this simplest statistically non-trivial situation. And what you see here is the so-called doubling rate, how fast you can double your capital relative to a optimal player or an insider player who knows what will come out. And so what you see here is that if the chooser is choosing always A, then you can always double. You are not worse than the insider guy, because the insider doesn't have extra information. If it always chooses B, then again, you are not worse than the insider. But if it's in between, then the insiders has some more information than you, and you will get less doubling factor than the optimally achieved. Okay, and then a meaningful question, actually, so this will be the Nash equilibrium, is to find the minimum of this doubling factor. What I need to stress here is that in the Bayesian game, we assume that the utility function is logarithmic. So this is baked into this Bayesian game. Okay. Okay, and just if you're curious, the minimum is where P star is 1/√5. And fun fact, the splitting ratio is the golden ratio. Okay, so so here you can have this nice theorem about, so you can do this very similar ansatz, you can do similar calculations, and here you can have an exact theorem about these. And what you have the same hypergeometric probabilities because of the sequence choices and the sampling. What is interesting is that the splitting ratios follow Bayes' rule. Okay, so this is not what we assumed. This is a theorem. This is something what comes out. It's derived. And then you need to find the unique minimum of this doubling factor expression for general NKAKB. Okay. Okay. So here I just show some examples. Here is some relatively big game where it's not trivial to find this minimum. The minimum is actually quite close to 1/2. And here you see what are the optimal splitting ratios as a function of K. These are not that interesting. These are sanity checks, basically, okay, to see that we don't see anything weird. Well, now we see something weird. So these have a bigger resolution. I'm sure these don't look like this. Okay, please see the paper for better resolution. You can calculate the priors, these P stars. Then I just showed how the splitting ratio would see in this game and the doubling rates. Again, nothing that extraordinary, just sanity checks. Again, you can see how these splitting ratios would change for different a number of ones. The red ones are the areas where it doesn't make sense because you surely know what will come out. Okay, thank God these have good resolution. So these are bigger games. Here again, you see the solution of 5,000, around 5,000 games. What is interesting maybe is that these prior probabilities are very, very close to one half. Very, very close. Only in the edges there is some deviation from significant. I mean, I don't want to use this term, but considerable deviation from one half. Okay. What emerged here? So what emerged here, just from game theory, is Bayes' rule, basically because of the logarithmic utility function. Exchangeability, this was very central for definitely, for example. And it comes from this randomization of both players, basically. Shannon entropy appears just naturally because of these logarithmic utilities. So I didn't mention, but this G, what you need to optimize. So this delta G, this can be interpreted as conditional entropy of the parameter assuming the data. Okay. And yeah. Okay. So if you're familiar with this, this is a little like a reference like prior. If maybe I don't want to. If you're interested, I'm happy to talk about it. And again, emergent probability distribution and interpretation of mixed strategies, similar what we have in Fisher games. Okay, maybe now I just, because we don't have much time, I just go through what I have and I let you choose. Okay, what do you want to hear about? So one thing is the limiting cases. First, you can go with the length of the sequences to infinity. That's how you get the so-called binomial games. I call it binomials because the distributions, the hypergeometrics became binomial. Then we can talk about the limit where you have binomial games and you go with the number of samples to infinity. These are both interesting and boring. Those are boring because then basically you will know for sure what's going on. But they are still interesting because the precise equilibrium values are having a quite intriguing behavior there. So I can talk about these oscillations and stuff. Okay. Then I can talk about statistical games, where basically you change the logarithmic utility function to something else, which is called either elastic or power utility function. And if you're interested why those are special, then you can go to Appendix E. And I think it's fascinating. I'm very happy to talk about that. And then we can talk about unification. How can you unify these Bayesian games with Fisher games with this isoelastic utility functions? How you can tune this extra parameter what you have there. And in the one end, you get the Fisher games, and on the other end, you have the Bayesian games. And I can talk about some philosophy as well.
Maybe, given that we've got about 5 minutes, maybe you can talk about the philosophical part.
Okay, let's talk about the philosophical part. Okay. So my statement is that a lot of features in statistics can be derived from a very simple framework where you say that, okay, let's assume that the states of the world is finite. We can relax that, so that can go to infinity. It's not that crucial. But let's say that there is this theta deal there. Let's say that we have some actions. Again, for simplicity, we can say that it's finite, but we can relax that. And let's say that we can do basically a kind of scenario analysis. We can find out what kind of utility we would feel if we would do A and the world would be in state theta. Okay. And if we do this, then Bayesian approach would be, and then if you need to do a decision, then the Bayesian approach would be to imagine a prior there, or come up with a prior on these states. What I suggest is to, let's imagine that there is an opponent, there is an adversary, but it's not purely evil. Doesn't want to purely make you cause you harm. It just wants to increase your regret. So what is regret? Regret is the difference between the optimal move and the actual move. So if you imagine that this opponent is feeding on your regret, then it actually motivates you to try out things, because there is this fearing of missing out. Basically, this is regret is the formalization of the fearing of missing out. And it will motivate you not just to play safe, but to explore. And so this is the, how to say that, human language telling of this thing. But then you can investigate this mathematically. You can say that, for example, if you imagine, if you put there a fictional player on the other side, then this have the same symmetries what a Bayesian decision rule would give you. And you have these different statements which I think shows into this direction. And what I'm saying is that it would be nice to investigate further what this kind of framework would give you. And that's basically the philosophical part. And all what I said could be framed in this framework. I chose a very special game, so-called symmetric game, where it doesn't matter if you assume a zero-sum game or a regret based game that would give you the same. That was my trick. That's why it's a toy model. You can do the same things when you have a general utility matrix and see what would be the consequences and what would be the suggested strategies there. And so my suggestion is maybe you could build up statistics from this relatively concise principle and do approximations only where you cannot do better. So we have, in physics, we try to write down first kind of an exact equation and then mutilate or use approximations to get some results. But it's good to remember that what was the exact problem what we wanted to solve. So that would be the philosophical part. Okay, and then I don't know. Tell me if I should end or have questions. Otherwise, okay, thank you for your attention. And if you want to drive back to any part, then please, I'm here to answer your questions.
Thank you. Thank you. Questions?
These Fisher games, people haven't studied equilibrium before. So
Well, it's always a very hard question if it was studied in the past or not. Citing 70 years old papers and 50 years old papers. Who knows what's in some shelves and desks and obscure Russian papers. I have an impression that it wasn't investigated like systematically. My guess is that it's mainly because those are degenerate games, and in most game theory textbooks, they assume that the game is non-degenerate from the second page. So maybe that's a factor. I'm not sure, but I'm not aware of any systematic investigation of this. Yes.
So I saw in your previous slide, you said this can be linked to data compression or model compression. If you like give a very brief summary of that.
Yes. So yeah, so here are these things. So what we did here is we gave reward to the guessing player based on if she was able to guess the model right. You can imagine that could be a data-centered approach as well. Maybe she can sample something and then she needs to predict the next sample. That would be an inferential risk. And then you can also play another game that you can take a sample. Then you have to come up with a coding protocol or a compressing protocol, and you need to compress. Then you need to apply this protocol to the yet unknown sequence, and that would be also a valid game, and you can calculate things there. And so the results can be close to each other, but not the same. And so if you're really interested in the nuances, then you should really spell out what you want to do.
Any more questions, people from home or online? If there are any questions?
I don't know. Can you hear me?
That sounds.
Go ahead.
Yeah, no, it's good. Can you go to the oscillations? So I have a question regarding the oscillations. So that means that for some games, there's basically in the limit, there is no, like it doesn't converge, right? Now, can you bring that somehow back to the philosophy? Because like that kind of, that it still doesn't mesh in my mind how that is possible, because kind of saying that there's no optimal probability at infinity.
Yeah. Yes, so this goes back to the statement that these are both boring and interesting cases.
Yeah.
And so these are boring because in the limit, when n goes to infinity, you will guess surely A or B. So it doesn't really matter what this equilibrium P star is. So every time if you are talking about convergence, you need to specify in what kind of metric you are interested in the convergence. And here, if you would take, for example, splitting ratios, they would uniformly converge either to 1 or 0. So these are the so these are interesting questions from mathematical point of view, but from practical point of view, this is basically meaningless. I mean, if I go to a person and start to talk about what to do if you have a 1,000-long sequence, I mean, he will know for sure what he should do.
But in real life, like we still use just the Bayesian approximation as if we would have infinite data at some point. So nobody just thinking about 1,000 data points in that sense, and then using the correction.
Right, but my point is that so I came up something which is called this independence tax. So how much money would you sacrifice if there would be somebody who is not 100% aligned with you, or who has the same heuristics what you think are optimal, if he or she would invest in your money? So you could have somebody who is acting on the behalf of you. And for example, in this Bayesian case, if you have a lot of data, then I'm not that bothered if some other person would go there who has different priors than me. So any prior can actually work in this n goes to infinite limit, which is not exactly 0 or 1. Because in the end, how to say, the data will speak much loudly much more loudly than the prior, and that's how it doesn't really matter.
Okay. Yeah. Yeah, that's helpful. Thanks. Yeah.
Yeah. So I think this is interesting, both interesting and boring, because it's interesting how it goes, but if you are interested in the actions, what I try to advertise here, that those are the most important aspects of a framework or a theory, then those start to be more and more meaningless as you have more and more data.
Right. Yes. Makes sense. Thank you.
Any more questions? If not, let's thank Joseph.